All right, so we did the left method and the right method, and what else could there be? Well, how about compromising between them? So there's something called the midpoint method, which I would like to call the horizontal midpoint method, because there is something else that makes more sense as the vertical midpoint method. So instead of using the 0 or the 0.25, we're going to use the value in between those, the horizontal midpoint, which is 0.125 here, and use that as the height of the box, and draw the box like that. I guess my axis wasn't quite straight, but that's okay. And then what's the midpoint between 0.25 and 0.75? It's 0.375. And I'll go up to the curve from there, and then I'm approximating the curve as constant in that region with that y value. And what's the midpoint between 0.5 and 0.75? That's 0.625. So I'll draw a point on the function there, approximate the function as constant in that region with that y value. And then our last one is 0.875, and approximate the function as constant in that region with that value. So would you say this looks better or worse than the other drawing we were doing, the left-hand method or the right? To me, it looks better. It's a little more complicated, but this box isn't entirely below or entirely above. Would you say this is exact now? We kind of hope it is. It turns out it's not for x squared. Let's remember this is x squared. So it looks better than left or right. It's still not exact unless unless the function is linear, then it is guaranteed exact. And I'll let you think about why. So it's guaranteed exact if the function is linear. Is it clear whether this is an overestimate or an underestimate? I'd say it's not clear initially. We'll figure out later how we can say whether it's an overestimate or underestimate, but we'll just say it's not immediately clear. If it's a LB or a upper bound. And for some functions, it's basically impossible to say. So I guess we can say we've got some kind of bullet items here. You might guess that since we're averaging the x values, we would get an average of the left-hand method's answer and the right method's answer. But it turns out you basically don't usually. So this is not the left method plus the right method over 2, usually. And what can we say about this in spreadsheet form? Well, you might have been wondering why I was starting in column C before. Now we'll see, because we could say column A is like the x value that each box starts at. Column B is the x value that each box stops at. And C is the midpoint of those two values. So we'd say like from 0 to 0.25, and here I could say equals average of those two values. And that would give us the 1.25 in that first case. And then column D, we could say f of x midpoint. So that would be what? If this was row 6, that would be C6 squared as before. Then you'd have the width. You'd have f of x times the width. And you'd have your running sum. So don't stress about doing this all in a spreadsheet. I suggest it as a way to organize calculations, but you can just do it all on paper with your calculator if you want. But the key idea here is we're taking the average of two x values, so we're taking the horizontal midpoint. So far we've talked about the left side method, the right side method, the midpoint method, but we were using pretty chunky boxes, 0.25 out of 0 to 1 each time. So how could we get better answers? We know we haven't defined the real area under a curve yet because we had overestimates and underestimates. So how could I get better answers when I have a box like this? Well, you might say, let's draw another box that doesn't overshoot as much. So if I drew a box that was half the width, it wouldn't go all the way up here, it would go just there. So we would only have this area as overshoot and not that area. And then this box would stay where it is, and that would be its overshoot, but then we wouldn't have this area as overshoot. So that would be for the right method for x squared basically. Or if we used a half width box here, that box could come up here and over, touch the function there, and then we would have less undershoot, right? So using skinnier boxes leads to less overshoot and less undershoot. And what can we say about that? We'd like to use boxes of what width? Well, we use boxes of width 0.25, 4 of them. Better would be what? Maybe, how about cut the width in by a factor of 10? How about 0.025? How many boxes would we have them? 40 of them? Or even better, how about 0.0025? Just start packing the zeros in there. That would be 400 of them. Obviously we could put more and more zeros in there. What would the best possible answer be that would have no overshoot or undershoot, hopefully? Boxes of width 0, which would be a good trick. And how many of them would there be? Well, if we just continue this process, we would be using an infinite number of boxes, which would take a while even on a fast computer. So instead of doing that actually numerically using Excel or Python or something, hopefully we'd have some way to do that algebraically where we wouldn't end up actually sitting and summing stuff all day. So we want to see what happens as the box widths go to 0, or as the number of boxes goes to infinity. But we would need a formula for the area of all those boxes as a function of the number of boxes. That would be handy. So I need a formula for the total boxes area as a function of the number of boxes. So that might be what we talk about next.